Okay, so we've looked at a few different ideas of how we're plotting graphs. And I guess our base quadratic and parabola is y is equal to x squared. In the previous chapter, you've been familiar with a quadratic formula, y equals ax squared plus bx plus c. What we're going to do is we're just going to slowly build our way towards that direction. But firstly, looking at y equals x squared, and our that's just a rough sketch of what the parabola looks like. This is your x-axis, this is your y-axis. There's nothing really special about this other than it's just a upright parabola, goes through the origin, which is in the middle, okay, where the coordinates are 0, 0. But we're going to manipulate this formula or this structure over the next few videos, adding a few different key features and seeing what happens. And in this case, we're just going to add a value of a coefficient in front of x squared. And then we'll just see what happens. And so you build an understanding of all these changes and alterations as we progress. Probably doesn't really make sense right now, but we'll put it into practice and it will start, connecting and making sense to you. So let's get straight to this here. So what I've done is I've put in a series of quadratic equations, and our first one is y equals x squared, as we are familiar with. So when x is 1, y is 1 because 1 squared is 1. But then when x is 2, we could see that 2 squared is 4. When x equals 3, we can see that x is 9. If I just hold there we go. And we continue exponentially, okay? Continue, and then 4 squared is 16, 5 squared is 25, etc. Okay, but what would happen if we had 2x squared? Okay, so 2x squared would change things and it would appear as so. Okay, all of a sudden we have what would you say, a steeper, skinnier parabola. Now, if you were to revert back to linear equations and straight line graphs, the greater the gradient, the steeper the graph. So you could kind of see a similar pattern here. The bigger the number, the skinnier the parabola is going to be. And in the opposite, if anything was less than 1, then you could see that the comparison is probably a bad choice of color. But if I was to toggle on and off, you could see that the parabola is a lot wider than the traditional just x squared. So the greater the number, the skinnier the parabola. The lower the number, especially going into fractions, will make it a fatter, a wider parabola. So another word to describe it is dilation. So let's just go back here. So if a is greater than 1, we have, I'll just put in words, skinnier parabola. And then if a is less than 1, okay, or we could say if a is greater than 0 but less than 1. So in other words, in a fraction, in a proper fraction, sorry, then we have a wider, fatter parabola. Okay, and this affects dilation. Okay, so dilation talks about how wide or skinny certain things are. You can even think about how your pupils in your eyes dilate as the sun, as you enter into a room that's darker or lighter. So the more dilated your eyes are, the pupils open to let more light in when it's in darkened conditions, but then when it's really, really bright, the dilation closes in to let less light in because it's quite bright. So it's just, I don't know if that kind of analogy and connection helps, but dilation, wider or skinnier, is basically the description in the effect. So what we have here in terms of our graphs, we've just compared what it's like to change things up. So I could easily make this into a 7, and you can see that the graph already becomes even skinnier again. Well, I change it to 77, not just 7. So let's change it to 7. You could see that it's getting a little bit wider. If I were to change that to a 3, then it's wider again. If I make that to a 2, then it's even more so. 3 and then a 2. Okay. Now let's move on to the negative. So what happens if we make the coefficient of x squared negative? Well, it flips it upside down. So previous videos, I talked about an upright parabola and an inverted parabola. And so the negative value makes it inverted. It just flips it, I guess, reflects it around the x-axis. And you could apply the same thing when it comes down to increasing or decreasing that coefficient in a negative value. So negative 4 x squared would, number 1, be upside down, and number 2, going to be quite skinny. So what we have in the purple, we do have an upside down parabola, and it is skinnier than y equals negative x squared. If we had negative third of x squared, then we have a value that's less than 1, greater than 0. So that's going to be a wider parabola, but still upside down. So do we have that? Yes, we do. It's wider than y equals negative x squared, but it is also inverted just like y equals negative x squared. So that's just the first thing that I'd like to describe about dilation. That's all you need to know. We're going to build onto the different features in the consecutive videos. But I'd like to finish off with one question just to help, I guess, consolidate your understanding. So here we have a question in regards to a skate ramp. And here we have, I guess, the ramp being that U shape. And the start of the ramp is at coordinates 3, 6. So 3 being the x value, 6 being the y value, and I've kind of attached the ramp to a Cartesian plane to give some visual description and illustration to this question. Now, the question's asking what is the formula, or what's the equation for this ramp giving that shape? And essentially what we can do, we know what the x value is, we know what the y value is, we just don't know what the a value is. So if we just substitute these values that we're given, so y is 6 when x is equal to 3. Okay, so we have 9. So basically we have 9a is equal to 6. A is going to equal to 6 over 9, or 2/3. So essentially, what we need to do is re-substitute that back into A to get our value for our ultimate equation. Y is equal to 2 over 3x squared. If you want to check and see if what you've done is correct, then all you need to do is re-substitute your values to see if it fits. So again, we're going to put x as 3, and we're hoping that the answer is 9. Okay, so 3 squared, 6. If we substitute x for 3, so we got 3 squared, that is 9, and we multiply it by 2/3, and Let's go 9 over 1. So assuming that you are familiar with multiplying fractions, 2 times 9 is 18. Divide that by 3 is equal to 6. So that does fit. It does check out. It's probably a really good way to make sure that your working out is correct. But that's how you would answer that question. Okay, hopefully that helps you guys today. We'll move on to the next one, next lesson, where we'll add another feature to this quadratic function.